Okie dokie, so we're back. We're back to video here. I really don't like doing recorded lectures especially for organic, because it tends to be a very dynamic course in terms of, as I introduce these topics and you guys ask questions about it, kind of steers how the discussion goes. But here we are for now. If this continues, then I might have to become clever and think of a different way to do class. I don't know quite yet, but given that we have very short amount of time to do this, and that I had an 8 a.m. class and then you guys right after to kind of accommodate, we'll do this for today, and we'll see where things go from here, right? But anyway, what we were dealing with last time was we had finished our discussion about E2s, and we had moved into our discussion of E1s. Now, if you recall from our previous course, class, I should say, that E1s, now we're dealing with formation of carbocations again, okay? We said when we have a good leaving group, like a halogen, bromine, iodine, that kind of thing, what can sometimes happen is as we add energy into the system, that leaving group can leave, okay? And we end up with a carbocation and all the shenanigans that goes along with that. And then a weak base can come by, grab one of the hydrogens next door, and we can end up forming our double bond, okay? So at the end of the day, our product at the end of an E1 looks a lot like the product at the end of an E2. But not everything is the same, right? We have a carbocation, so we have rearrangements, we have a weak base. All this stuff means that this is going to be a slower reaction. Like E1s are really not that fast, right? E1s are really not that fast. So what we need to talk about those reaction profile diagrams. And a reaction profile diagrams is kind of like, let's say, the Google Maps for starting the reaction and getting to the end of this reaction here. It's going to be a pathway, right, for where we start and where we end up, all right? To draw a reaction profile diagram, you're going to have to know your mechanism, okay? Because our mechanism is going to give us important information that we translate into the diagram itself, okay? So we already have the mechanism for this here. So I'm going to draw us a small reaction profile diagram down here in the corner, and then we can talk about the individual parts of it, okay? Whoops. Let's do this. So a reaction profile diagram is just a graph of the relative energy at the different parts of a mechanism, okay? So just like with any graph, we have to start somewhere, we have to end somewhere, okay? We start at the beginning with our starting materials, and we end at the end with our products, okay? Now, this first part is kind of arbitrary. We're going to start down here, and let's say we're going to end up here, okay? And I'm just going to move this out of the way. Bring that back, okay? So how do I know where things start and end? Well, we don't really know unless I give you guys some information, although we kind of have an idea here, right? We end up getting rid of sigma bonds and making pi bonds, so it probably makes sense that our starting material is higher in energy than our products are higher in energy than our starting materials. That's not so important, okay? But now we need to figure out the pathway to get from here to here. And that's where our mechanism comes in. So how many steps are in our mechanism? Well, there's two. We have one, right? Formation of the cation, and two, the elimination part, which makes our double bond. So if we have two steps in our mechanism, we have two hills to climb, okay? So we're gonna have two hills to climb to get from our start to our finish, okay? Now, not every hill is of equal height, right? Not every hill is of equal height. Hill number one is our rate determining step. And our rate determining step is our highest hill, the biggest mountain that we have to climb. So it needs to be the highest hill here, okay? Now watch, how's that going to look? I'll switch to red here. Okay? And then for part 2, all right. So hopefully with the colors there, you guys can kind of start to see what I mean with this. So part 1 is the first hill. And when we're talking about climbing a hill, we're always from where we begin to the top. Okay? To the top of that hill. So really, what we should be looking at is this. Okay? Versus that there. Okay? Let me zoom in and get to have you guys take a peek at it. Okay? So from the bottom of the hill to the top, that change in energy there is what's going to be important. All right? Now, each of those energy values we would call the activation energy, okay, to get the reaction going, right? But the biggest hill is our rate determining step. So if you imagine yourself riding a bike along this, mountain range, this first step here is going to take you the most time to get over the highest hill that you guys have to climb, right? That kind of thing, okay? But this is what a reaction profile diagram looks like. Now, what other information do we get out of this, or what are the other components for it? Let's see here. Black looks good. At the top of the hills, those are our transition states. And our transition states are where bonds are being broken and where bonds are being made. Okay? So at the top of those hills are where bonds are being broken and made. In the valley, let's see here, yellow, yeah. In the valley, oh no, I ran out of room. Let's redo this. In our valley is where our intermediates are, okay? We only have one intermediate because we have 2 steps. We start, we do step 1, we get to an intermediate. We do step 2, we get to our products, right? So 5 important things we should get out of this. We start, transition state, intermediate, transition state, product, okay? That's all it really comes down to. How many hills we have are the number of steps. The valleys are how many intermediates we have there, okay? So our intermediate in this case is a carbocation. Those tend to be very energetic, high energy intermediates, right? Although we try to make the lowest energy carbocation, and so sometimes we have this confusion between high and low energy there. I get it, okay? But this is a reaction profile diagram. They're useful for telling us some things, and the book uses them quite a bit to kind of determine which reactions happen in what case, right? But you have to draw your mechanism to be able to do these, okay? All right. So now that we've talked about our E1 and our E2, what we need to do at this point is introduce the next set of reactions that we have to deal with. So eliminations, right, are all about forming double bonds. So we learned about additions, we learned about eliminations. Now what we're going to talk about are substitutions. Now, much like what we discussed with E1 and E2, we're going to have 2 substitution reactions to discuss or to think about or to wrestle with, okay? And what we're going to have are, appropriately, we're going to have something called SN1 and SN2, okay? So substitution, nucleophilic, unimolecular, SN1, and substitution, nucleophilic, bimolecular, SN2, okay? So we're going to have these two steps right here, okay? Now, what we're going to do here is kind of the way we approached eliminations. I'm going to talk about these individually, and then we're going to come back and we're going to mash all four of these together and say which one happens the most frequently, okay? So these four mechanisms that we're dealing with, the SN1, SN2, E1, E2, they're oftentimes going to be in competition with each other. And our job as a chemist is to sit there and analyze and say, well, I know all four of these are happening, which one's going to happen the most frequently and why, right? Which one's happening the most frequently and why? So we really have to start to pay attention to the clues and the ideas and reaction conditions that get presented as we go through these, okay? So let's talk about SN2 first. Let's give some bullet points, right? So it's a substitution. Okay. So a substitution just means we're going to take one functional group and swap it for another. Okay? That's all it means. We're going to have to take one good leaving group and we're going to have to swap that good leaving group for a good incoming group. That's all a substitution is. We're not getting rid of the leaving group directly to make an elimination. We're getting rid of the leaving group and swapping it for another functional group that's not an alkene. That might be another way of thinking about this, okay? So we're going to swap a leaving group for an incoming group, okay? The 2 means it's bimolecular, rate determining step. And so similar to what we thought about with similar to what we thought about with E2, we're going to have a single step, okay? And if you guys are already thinking about this and the brains are working, you're like, hey, wait a minute. You know, a lot of what we're writing down here sounds very similar to E2. I wonder if E2 and SN2 compete. Yeah, that's where we're going to get to, okay? So, but anyway, we'll don't worry, it'll all become worse, right? But first, let's just focus on this, right? Bimolecular in the rate determining step, right? So we have, what we'll see is a single step, and there's going to be 2 molecules involved with this, okay? Now, let's put some limits on this, right? We'll need a good leaving group. And remember, if we were together, which we're not, right? I'm speaking to an empty room. I don't know if you guys know how awkward this is. I have to project energy to a bunch of chairs. Right? So, anyway, right? So we have to have a good leaving group. Now, again, a good leaving group means something that can handle a negative charge, or even better, something that becomes neutral as it leaves, okay? So we'll see a couple examples of this as we go further along in our careers in organic chemistry, okay? But a good leaving group means we're just stabilizing a negative charge. We can disperse it, resonance and squishiness and inductive effects and all these other kind of things that go into dispersing or spreading out a negative charge, right? So we have to have a good leaving group. We're going to have a good nucleophile coming in. Okay? All right, so now we've got to pause here for just a second. Okay? So we need a good leaving group and we need a good nucleophile. Now, what is a nucleophile? Right? And so I'd spend some time here kind of asking you guys, okay, tell me what makes a good nucleophile. So pause it and think, I guess, I don't know, right? But a good nucleophile, remember, a nucleophile is something that wants to go after a positive charge. It files some nukes, right? Files with the P-H-I-L-E, right? So it wants to go after positive charges. So if you want to go after positive charges, then you yourself have to be negative, but not too negative, okay? And what do I mean with that? Well, a good nucleophile for us is going to be a soft negative, a squishy negative, a polarized negative, a spread out negative, a delocalized negative. A weak base would be a good example of a good nucleophile. Okay? Now, let me pause here for a second. Okay? And I'd walk you guys through an example like this and say, here we have our good old buddy ethoxide, right? An oxygen with a negative charge. Is this a good nucleophile? Right? And we'd sit here and say, does it have a negative charge? Yes, it does. But it's a localized negative charge. So is this a good nucleophile then? And we would still say yes. Okay? Because if you're negative, you're going to go after something positive. Okay? So this is a good nucleophile and a good base. And that's where some of this competition starts to come in. Okay? Good bases can be good nucleophiles. Okay? But not all good nucleophiles are good bases. That's going to be the difference. Okay? The difference is that negative charge localized or not? That's going to be one of these key clues that we have to start to pay attention to figure out what's going to be going on with this. Okay? Let me take a walk over here real quick. All right, sorry about that. I had to kind of adjust something here. So, a good nucleophile, okay? But also a good base. Now, if you are a good base, we mean you are a strong base. And if you're a strong base, you're going to want to act like a base first, okay? One of these core ideas to think about is that acid-base reactions are some of the fastest reactions to happen, some of the quickest reactions to happen, okay? And so if you're a strong base and you have any acidic hydrogen around, you're going to go after that acidic hydrogen, okay? That's just the way it works. And so acid-base reactions tend to be the first reactions to happen. They tend to be the quickest reactions. And if you're doing a reaction with a base, we tend to favor more the elimination, okay? But we'll get into that in just a second there, all right? All right, I'm going to take a quick pause here and we'll pick this up in part 2, all right? So.